All right, so we're going to do, kind of mention this relative motion problem that I just drew on the board. An example, as an example of something that's a little more complicated than those one-dimensional cases that you can just intuitively figure out. So what we have is we have a car driving along the road going 32 meters per second. And say it's raining and the raindrops are falling with a speed of 13 meters per second. And say there's no wind, so the rain is just falling straight down. And what we want to know is the velocity of the rain relative to the car. Now notice when I wrote down these values here, I wrote these down without the vector signs because these are just the speeds. This is just how fast they're going. The car's going to the right, the rain is falling straight down, both relative to the ground. So how do we actually solve this problem? Well, what we want is the velocity of the rain relative to the car. And so let's use our rule to break it up into two pieces. So we start with R, we end with C, the two in the middle are the same. And so let's start with velocity of the rain relative to the ground. That's this vector here. Now what about the velocity of the ground relative to the car? The velocity of the car relative to the ground is to the right. So the velocity of the, I don't know if I said that right, the velocity of the car relative to the ground is to the right, and so the velocity of the ground relative to the car would point to the left. Okay, so we kind of accurately drew these, or at least somewhat accurately. Rain is falling down. Relative to the car, the ground is moving backwards. And again, you can see that if you're driving. If you just look out the window and say there's a tree, from your perspective, the tree is moving backwards. So, and now, if we just add these two vectors, that's equal to velocity of the rain relative to the car. So just from our equation. Velocity of the rain relative to the car, that's rain relative to the ground, and ground relative to the car. So we have this nice right triangle here. And I'm actually going to draw it as a triangle without the vector, like without the arrows. So here, the velocity of the rain relative to the ground is 13 meters per second. And this is the ground relative to the car, that's 32 meters per second. And so what does it mean to find the velocity of the rain relative to the car? Well, it has a magnitude and a direction. So we can pick one of these two angles for the direction. Let's just pick that one. And then we want to find both the magnitude here, so the speed of a raindrop relative to the car, that's the hypotenuse, the raindrop relative to the car. So we use the Pythagorean theorem for that. 13 squared is 169. 32 squared, not sure, 900 and something, but let's get it a little more accurately. Oh, 1024. So if we add those up, we get 1193. Square root of 1193. That's 34.5 meters per second. So that's how fast the rain is moving relative to the car. So it makes sense that it's faster because you're moving towards the raindrops. And again, this angle kind of makes sense as well because you're moving towards it. So from its perspective, the raindrop should be moving towards you, and it's also falling down. So yeah, it should point in that direction, but we want to find the angle. And again, let's use tangent of theta. So that'd be 32 over 13. And I use tangent because, that's a calculated number. It's possible we screwed that up. But these two were given. We'll say for doing it that way. And note that I did not include units here because they're both in meters per second, and so they would cancel out. It's very important because you never want to say tangent of theta is equal to like 6 meters because that just doesn't make sense. So now let's take the inverse tangent. And again, you always want to be careful with inverse trig functions. But in this case, we're definitely getting an angle between 0 and 90 degrees. That's what we want, and that's what we're going to get. So what I'm getting is 68 degrees. So that would be the angle. So the rain, it looks from your perspective, this is that you're moving pretty quickly here. And so from your perspective, the rain is almost moving like horizontally to you. I had a teacher once, actually a history teacher. So he was driving a convertible once and it was raining, so he just sped up. So if you look at the windshield, if the rain is coming at an angle, it's basically you're going to have this kind of shadow here where if you're in this area, you're not going to get hit by the rain. So like if you're stopped, the rain's going to fall straight down and hit you. But if you're driving, the rain's going to be coming at you at an angle, and so this windshield can actually block it from you. And so you can stay dry in a convertible if you're going fast enough. All right, so that's just one example of a relative motion problem. And we do want to practice this some more, but we'll do that during class. Let me think about that for just a second. On Monday we're going to go review vectors. And I think I'm going to assign this on Tuesday. So on Wednesday we should be able to review this. Okay, so I think I'll just kind of stop it here, and then we'll review things in class.